you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, Mr. T here with another tutorial in our series on quadratics. And today we're going to be talking about, instead of quadratic equations or quadratic functions, we're going to be talking about inequalities. So we've got an inequality symbol here instead of an equals. And we have two kinds. We have ones that have two variables. So we're looking for places on a coordinate plane that make x and y values that make this statement true. And we have inequalities with only one variable that look like this. So we're looking for values of x that make that true. So in this, we're going to show our solutions on a coordinate plane because we have two variables, and on this we will be using a number line. So let's look at an example of each. The procedure is going to be very similar to when we did linear inequalities in an earlier unit. When we did linear inequalities, we drew a boundary line based on the linear equation that we had here. This is, since we have an x squared as a quadratic. And if you remember, we drew that line, our boundary, using either dashed or solid lines, depending on our inequality symbols. And then we shaded above or below the line. So the procedure is going to be identical here, except our boundary, instead of being a straight line, will be a parabola shape. So we have to graph this parabola, and whatever method is appropriate. We could use the standard form here. So if we graph in standard form, our h is going to be negative b over 2a. So negative b is 2, and 2a is 2, so we get 1. And the k value, if we plug that 1 into here, we're going to get 1 squared minus 2 times 1 minus 3 is negative 4. So we know our vertex is at 1, negative 4. And this is our axis of symmetry. And from standard form, we know this number is our y-intercept. So I'm 1 to the left, so I have another point here, 1 to the right. So I've got 3 points to draw my parabola shape. And since we have a regular inequality, I want to draw that as a dashed parabola. So let me just make a dashed parabola shape here. Oops, not very good on drawing the lines here. Let's see if I can get it going this way. Okay, so we have our parabola. And it says here, if we're doing a greater than, we want to shade above. So our solutions are going to be above this parabola. So that's going to be the shape or the area inside of the parabola. So in this case, our solutions are in this parabola shape inside the parabola. Now, if you remember, we can also, if you're not clear on which side to shade, we can always pick a test point not on the boundary. So if I pick the point 0, 0 as my test point and put that into the original inequality, so I would have 0 greater than 0 squared minus 2 times 0 minus 3. So I get 0 greater than negative 3, which is true. So that my test point is true, so I shade the area that includes the test point, the side of the boundary that includes the test point. So that's a quadratic with two variables, and if you know how to graph quadratics, it's quite simple. Now we're going to look at ones where we have one variable. Now ultimately we're just going to be using a number line, the x-axis, but in this method we're going to solve it graphically. In a second we'll show a second method. So we want to treat this side of the inequality as a equation, a y equals. So we've got a parabola and we want to graph it. Now this one I can see easily factors, and in particular, since we're interested in the x-intercepts, if I can put it in factored form, that's going to be the way I want to graph it. So I rewrote that. So that factors into x plus 2 and x minus 1. So on my number line here, if I take the opposite of this, negative 2 is a x-intercept, and here at 1 is a x-intercept. Now my vertex is going to be at the midpoint here at negative 1/2. And since A is positive, I know it opens up. Now I don't really care exactly where this vertex is, because for this method, we're not looking at the y values in particular in terms of what they are. So I'm just going to place the vertex here. I didn't calculate it. Remember, we could find the midpoint between here and here, negative 1/2, and plug that into here and get some fraction and get the exact value, but we don't need to know that. So I'm just going to sketch in the parabola here. Now, what this is saying here is we're looking for values of x that make y, since that whole expression is y, is less than 0. So we're looking for the values where y is less than 0. So that's here. But we're only interested in x values. So the x values are these x values that are associated with this part of the graph. And since this is less than, we would be wanting to, I'll have to make it big here, an open circle here and an open circle here. So we are looking for an open circle at 2 to here. I should have done, I guess, done the x-axis stuff here in a different color. So we've got an open circle with a line in between and an open circle, and that boundary is at 1 and at negative 2. So if I write an inequality for that blue number line graph of an inequality there, it's going to be x is between negative 2 and bigger than 1. And if we can sketch a graph of our quadratic, that's a fairly simple way to get our solution. Again, this is our answer here, an inequality statement. Or on a number line graph, if we graphed it on a number line, again, we would have negative 2, 1, open circles here and here. And that would be the graphical solution here. Now, we may not want to go to the trouble of having to graph the function. And so if we have an inequality here, our first step to do it analytically is, again, we want to find x-intercepts. So we're wanting to find or solve the equation. Now, from our last unit, we learned a bunch of different ways of solving this: factoring, quadratic formula, completing the square, you name it. So again, this is the same problem we just had a minute ago. So we know this factors into x plus 2 times x minus 1. So my x-intercepts are at negative 2 and 1. So we're going to organize those on a number line. Now we know from the behavior of a parabola that between these two x-intercepts, since these are the only intercepts, this function can't wiggle. It can't be partly up here and partly down here. To have the function, say, go up here and then back down here, we would have to be having another x-intercept. And we know these are the only x-intercepts. So we need to know in each of these test intervals, so let's call this, test intervals, the points in between here, we need to know, does that make the inequality true or false? Does it make this expression positive or negative? So I'm going to pick a test point in each interval. So I'm going to pick, say, negative 10 here, 0 here, because that's an easy number between, and I'm going to pick 10. I'm picking numbers that are kind of easy to calculate. Now, I need to find out, since we're looking for this expression less than 0, I'm looking for where the expression is negative. I don't care if it's negative 1, negative 100, negative whatever. I just want to know if it's negative. Now, the straightforward way is to take your test value and plug it into the equation. So I could plug in here negative 10 squared minus 10 minus 2 and calculate that. Here I'm going to get 100 minus 10 minus 2 is positive 88. So in here, my expression is not negative, it's positive, so this part's false. If I put 0 in, I've got 0 squared minus 0 minus 2 gives me negative 2, so that is negative. So this part's true. And over here, I get 10 squared plus 10 minus 2 is 108, and that's positive, so this is false. So my solution goes from negative 2 to 1. And again, we could write that in inequality form as shown here. Now I just want to give you a little shortcut. This works, and we use it quite a bit in my calculus classes, is if I use the factored form of this, I don't really care that this was positive 88. It could have been positive 8, positive 0.8. It doesn't matter whether it just, we want to know if it's positive or negative. So the way I do this is I pick a big negative number over here. So if I put a big negative number into this factor, so this technique only works when the quadratic was factorable. If I put a big negative number into this factor, I get negative. And if I put a big negative number into here, I get negative. Because negative 10 minus 1 is negative 11. So negative times negative is positive. And we know that that is false. If I put 0 in, 0 plus 2 is positive. 0 minus 1 is negative. Negative, this is back-to-back factors. That means multiply. So positive times negative is negative. So again, that was true. And over here, if I put 10 in, I get positive, positive, and again, that's positive, which is false. So you can calculate as I did here, or you can just plug in if you're able to do this by a factoring and figure out using positive and negatives. So in any case, our final answer is here. So good luck on working these problems.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you